going to do something a little bit different. I'm going to put together a little electronics kit. I think electronics kits are great. You can buy them on eBay for like less than $1 each. If you search for the keywords DIY sweet, I don't know why sweet, but if you search for that, you'll find tons of them for under $1, and they're great for everything from just practicing soldering. If you haven't soldered before, or you need to get comfortable with soldering, buy these. And if you screw up the kits, doesn't matter. They cost $1. This one didn't cost $1. It cost a little bit more than that. This was actually, I don't know how much this cost. I got this as a gift. The other thing, though, but electronics kits are more than just learning how to solder too, because you can, as you get more comfortable, you can do other things. You can start to look at the schematic and try to figure out how it works ahead of time, to help, and then put it together and see if your understanding based on the schematic is how it operates. It's a way to sort of learn and reinforce your knowledge of how different electronic components work together. Another thing you can do is you can modify them. You can look at the schematic. Or you don't even have to look at the schematic. You could just look at the board and try and figure out how everything is connected, and figure out how you could modify it to do something different, from changing the color of an LED to changing the speed at which it operates, whatever it does. Changing how the interface is. If it's got buttons, change the buttons. See what that experience is like. Maybe there are buttons on the board. Run wires from the board to an external switch somewhere. And now, instead of pushing a button on the PCB, you've got to use a game controller or something. There's all sorts of ways to take a little cheap electronics kit and, learn and make more out of it than what it comes with stock. So, anyways, this is Brain Game, and it comes from Velleman, and I'll just put it together here so it comes apart pretty easily. And we can see it's going to be battery powered, 3 AA batteries. There is your PCB, all the electronics. Why they kept the resistors, these resistors, out of this bag, but the rest of them are in here, I'm not sure. I suspect it might have something to do with, they might be able to do variants on this, different LEDs, because I believe these, because there's 4 LEDs, we can see that on the picture here, 4 LEDs. So each LED needs a resistor, and if these are 470, which, do we see the colors? Those are kind of weak, but that looks like yellow, purple, brown. Yellow is 4, purple is 7, brown is 1, 4, 7, and 1, 0 for 470 ohms. Those are your LED resistors. They limit the current going through the LED. Too little current, the LEDs are very dim. Too much current, the LEDs burn out. Put that off to the side for the moment and see what we have here. This little sheet opens up. We have some basic soldering instructions, how to identify the different resistors, talking about diodes and their polarity here. You've got the symbol, you've got the diode, explaining how the diode symbol has that vertical line and it should match up with the band on the diode itself, for the silk screen here. The white printing on the PCB here is the silk screen. Switches, you've got your IC socket, so that's where the microcontroller is going to go. It talks about diodes, capacitors, all of this stuff. And we have a schematic. Now, this isn't much of a kit in terms of being able to reverse engineer, because all of the secret sauce, all of the magic is there inside of the microcontroller. So whatever this game is, which, by the way, I am not seeing any game instructions other than how to start it, I guess, with or without sound, and then you choose your level of difficulty, and then the game begins. And I have no idea what the game is. I guess we're going to find out together. But when we look at the schematic here, we can look at a few things, get a few ideas. We can see it marks it here as a PIC-12 microcontroller. It's a very, very common microcontroller. You could go on the internet and search a data sheet for that, and you could actually figure out how to reprogram it to do something else. You can build this, play the game, and then when you're bored of the game, you can go out and figure out how to reprogram this to do something else and have it play a different game that you've devised if you wanted. Looking at the schematic here, we have 4 LEDs. There are the 4 resistors right above it. You can see the LEDs have a little diode symbol, like over here, except they have little arrows coming out. That's to symbolize light exiting the diode, showing that they're a light-emitting diode. And we can see each LED also is paired with a switch, which is an interesting and clever trick here. This microcontroller has 8 pins. 1 pin will be for power, 1 pin will be for ground. That leaves 6 pins to do stuff with. You have 4 LEDs and 4 switches. That's 8 separate things you need to control, plus the buzzer over here. 9 separate things that you need to control, and you only have 6 available pins. So how do you do that? What they're doing over here is, what I assume anyways, is let's take this pin 7, GP0. We can see it comes over here. It's connected to this LED and this switch goes to ground. So what's probably going to happen here is, you can see the anode, the positive side, goes through this resistor and up to the power. This is the battery, the power rail here. It comes through here, through this LED, and then it either goes into the microcontroller or through to ground when the switch is pressed. So what's going to happen here is this pin on the microcontroller can be controlled to either be a high or a low. For a high, it's emitting electricity. It is essentially connected to the positive rail of the power line that's coming into the chip here. Or when it's low, it's essentially connected to ground through here. So when this line is connected to ground, electricity can flow through the battery, through this resistor, through the LED, through the microcontroller to ground. When the pin is low, that LED will turn on because electricity can flow. When that pin is high, it's essentially connected to the positive rail here. There's no place for electricity to flow. The voltage here and the voltage here are, for all intents and purposes, the same. There's no place, there's no force, electromotive force here, pushing electricity through to make the LED glow. So when this is high, the LED turns off. What's probably happening is this pin is switching between high and low very quickly. When it's low, the LED turns on. When it's high, what it's more than likely doing is it's also, once it sets itself to high, it then measures the voltage at the pin. And if the voltage at the pin is high, when the pin is set to high, then you know that there is no connection to ground. But if this switch is pressed and this pin is set to high, all that power coming out of that pin is going to go right to ground through the switch. So when it measures the voltage here, it's going to see that it's at 0 volts. It knows then that the button has been pressed. So this is switching back and forth between high and low. When it's high, it's checking whether or not the button is pressed. When it's low, it's turning the LED on. And it's just going to keep going back and forth through those two states, controlling the LED and then checking the button. And that is how, with one pin, you can have an LED and a switch on the same pin. Kind of cool. What else do we have? We have an interesting pull-up resistor here. That's what this resistor is pulling this line here up to the positive rail. It's called a pull-up resistor. If this was connected to ground, it'd be called a pull-down resistor. It's pulling up this line. So I don't know if that GP2 pin, and again, this is where you'd look up the data sheet here. It could be that GP2 pin doesn't have an internal pull-up resistor, so you need to put an external pull-up resistor, or who knows. We have our connection to ground here. We have our connection to the power rail. And we have this coming through a resistor over here to a transistor. This symbol here is the speaker. And in this case, it's just a coil of wire essentially hooked up to a cone. It's like a normal speaker. And what this microcontroller is going to do is it's going to send signals, rapid on-off signals, to this transistor. This transistor is going to act as a switch, turning power on and off to this speaker very rapidly, and that's going to cause it to vibrate and produce sound. There's an interesting thing here. They've included a diode here. I believe that's called a flyback diode. Because this is just a coil of wire, you get some interesting things happening electronically. when electricity is flowing, when the switch is turned on and electricity is flowing through the speaker here to ground, what's going to happen here is that coil of wire is going to have a little electronic charge to it. It's going to have a buildup of an electromagnetic field built up to it. When the switch turns off, there's no place for that electricity to go. And what happens is the voltage, you get a massive voltage spike here because it's trying to push all this electricity out and it's got no place to go. So the electrical pressure, if you will, keeps building up and building up and building up, and it can get to the point where it gets higher than the threshold that this transistor will not conduct electricity. If the voltage goes too high, it can jump through the internals of the transistor, it can break the transistor, and that would be bad. So they've included a diode here so that when this turns off, there is a path for the electricity. It can go back and just keep on this loop in on itself. Now, it dissipates very quickly. It's you don't have electricity running in a loop forever. There's resistances in the line, in the wire. The electricity very quickly dissipates, but that's what that is for. It's to protect this transistor and really the microcontroller from being damaged by those little high voltage spikes. Also, because of that little coil of wire, put a lot of electricity into it, and then turn off the switch, and it builds up voltage because it's trying to get rid of that electricity. That is how you can also do take a very low voltage, say a single battery, and create 3, 4, 5 volts of electricity out of a 1.5 volt battery to power, say, a flashlight or something. So if you ever see a flashlight that powers off of a single battery, it's doing something like this, except instead of a diode here, it has an LED. So the LED flashes on. In fact, maybe that's a mod that we can do with this, is that I will replace that with an LED. But if I do that, we'll figure something out. I'm gonna have to put a resistor in line so that it doesn't blow out the LED. Yeah, we'll figure that out. But that's an interesting mod. Then you can actually maybe see that flyback diode in action. Okay, that's 12 minutes of theory. We should actually get to putting this thing together. One other mod. Well, we'll start taking it apart, unpackaging this. Because I have an idea for another mod. I want to put all the hardware that I know I'm not going to need right away off to the side. So nuts and screws, all that stuff can go off to the side. We have switches. I like these switches. These are nice big switches. There's a screw. I'll group everything together. There are the LEDs, the switches, the buzzer. There's the socket for the chip. There's the PIC-12 itself. And it's probably, once they program it, they put a little stripe of magic marker on there to signify it's been programmed. A capacitor, a transistor. What kind of transistor? A BC547. Now what's interesting is that's a very common European transistor, so you kind of can guess this is a transistor that comes from Europe and Belgium. So signs of where the kit came from. We have a little tiny diode, and here's the big flyback diode that we're probably going to replace with an LED. Not sure how appropriate that is, but again, this is a kit. I don't know if it's appropriate to use an LED because what's going to happen is the voltage is going to have to spike above the forward voltage of the LED. The forward voltage, that is the voltage it takes to that needs to be across this diode before it'll start conducting electricity. This one will be about 0.7 volts, but for an LED, it's going to be about 2 volts. Is that too high? It shouldn't be too high. We could actually look up the datasheet of the 547 or whatever that transistor is. And we could look at what the breakdown voltage is between the base, the collector and the emitter, and that would tell us if 2 volts is too high and if it would break that transistor. But I'm going to guess that will be fine. This is interesting. It is just 2 strips of wire. What is that going to be for? Those are links? Are there links on this thing? I don't see. Oh, you know what that's for? I know what that's for. The battery pack here. Instead of normal wire, or instead of insulated wire, they're just using 2 leads, and that's interesting. Comes on this tape system. Comes in a big roll. That they make those kind of things. Cool. Just strips of wire. I might actually have to go see if I can buy those on eBay. LED resistors, and then 3 other resistors for other things. So we've got everything sort of sorted out here. Put that off to the side. The microcontrollers, the switches, we don't have to worry about those right now. Just put everything off to the side. So one other mod that I mentioned that I want to do is this kit comes with these 3mm red LEDs, which are, I mean, they're just tiny. They're just ridiculously small. There is no need for using LEDs that tiny. So what I'm thinking is I've got this. You can buy these off of eBay, again, for like, I have no idea, but only a few dollars. You get this package of a bunch of different LEDs: white, yellow, red, green, and blue. Now, you can pick your color, and I've got 3mm and 5mm. I want to use 5mm. What color? I could stick with red, or I could choose a different color. If I choose a different color, the LEDs are probably going to be a little bit dimmer because, again, these resistors here that limit the current through the LEDs. Right, in the schematic here, we're looking at these resistors. Their value was selected with red LEDs in mind. Each LED has a different power, different voltage, forward voltage that it takes before they turn on. The higher or the lower the forward voltage, the higher the resistor should be to limit the current through the LED. So a 470 ohm resistor is going to, well, we can do the math real quick, actually. Oops. So we have 4.5. We're going to do all sorts of math. So we've got 3 AA batteries. So that's going to be 4.5 volts. But then we're losing the voltage across this diode here, this D1. That's a reverse polarity, I think, protection. If you put the battery in backwards, you could break your microcontroller, could blow up. So, well, not, when I say blow up, I don't mean there's an explosion. I mean it just internally something blows out and the microcontroller never works. So that's there to prevent you from making that mistake. You don't need that. We could just wire that across and be comfortable with the idea that we know not to install this backwards. That would give us a little more electricity for the LEDs, make them a little bit brighter. Again, another mod we could consider. Or we understand that, maybe not us, but somebody in the future using this might not understand how to put batteries in a battery box the right way. And we keep that there to protect those future people. But anyway, so we're losing that, which is going to be, I don't know, maybe, I don't know if, I assume that's a Schottky diode, but the symbol is a regular diode, so we're just going to say it's a 0.07. Oops. Let's start over. 4.5 volts minus 0.7 volts for that, and then we're coming through the LED here as well. That LED is a red LED. It's going to have about 1.5 volts for a forward voltage. So we've got a total of 2.3 volts that'll be going through across that resistor that we need to limit the current with. 2.3 volts, we divide that by the resistor, and we see we're going to have about 5 milliamps going through those LEDs. That is more than enough. So 5 milliamps as it is. And you notice how close it came to 5 milliamps? So you can tell that the designers wanted 5 milliamps. They knew about that, and they knew what the forward voltage for that was, and they picked the closest value that would get them, of a standard resistor value that would get them to 5 milliamps. Now, let's go back to, if we use a yellow LED, say, we had 5 milliamps. Let's go right to the blue, 3 volts forward voltage. So we know we have 4.5 volts, right? And we're going to take the 0.7 from that thing, which it might be less. I have to look that up. And now we're taking away 3 volts for the blue. Now we're going to divide that by 470. And now you see we're down to 2 milliamps. So the blue LED will be half as bright, in theory, as the red LED. There are other things to consider about brightness. The different chemistries that make up the LEDs are inherently brighter or dimmer. So while the same current might not provide the same brightness, anyways, you get the idea. If we put a different color LED in there, do we consider changing these resistor values? Or do we just solder it all together? Man, this video is 20 minutes long already. And we haven't soldered a single thing. It's all been theory and looking at the schematic, looking at the design, and discussing options. And this is the beauty of these cheap little electronic kits, is you can spend, you can give yourself this 20 minutes of sitting around looking at it, figuring out how it works, what modifications are possible. Or if I had just started soldering this as soon as I hit record, we'd be done by now. And we'd have whatever the game is, we'd play it for 5 minutes, and then that'd be the end of it. We'd be confident in our soldering skills once we got everything soldered together, and then that would be that. Or we sit around and we discuss theory for 20 minutes and, help reinforce our knowledge of electronics. You can go either route with these electronic kits. That's why I like these things. All right. What am I going to do? I'm going to pause for a second and figure out what I'm going to do. Right. So a couple of things. First, those red LEDs I'm replacing with these yellow LEDs. I will not be changing the resistors. They'll just run at a slightly dimmer light level. I'm not worried about that. Because 5 milliamps is you really only need a couple milliamps. 5 is kind of bright. And in terms of space around the footprint, you can tell the silkscreen is recommending 5 millimeter diodes to begin with, LEDs to begin with. So I don't have to worry about them encroaching, the LEDs. I don't have to worry about them encroaching on any of the other components that are around it. So yellow LEDs is what I'm going to go with. I'm still working out how I want to do the flyback diode on the speaker. It would be a little 3 millimeter clear white LED, which will have a 3 volt forward voltage. But is that, well, before we get there, I want to show you if this tablet wants to turn on for me. Come on. Here is that little diode, this BAT85 diode that I was calculating the forward voltage off, assuming it was 7 volts, or 0.7 volts, that right there. Here's the data sheet for it, and we can see forward voltage is 400 millivolts max. It's a Schottky diode, which means it's got a low forward voltage. And 400 millivolts max forward voltage, so it's probably less than that. It's probably like 200 millivolts or something like that. So that just means that in my calculations, we're probably gaining another couple hundred another couple hundred microamps on the current going through the LED. No biggie. What I need to do now quickly is look up the BC547 and look at the breakdown voltage. Make sure 3 volts is not too high. It's not. I know it's not, but I'll look it up real quick. Here is the datasheet for the BC547 and a few others here that are all sort of in the same family. Maximum ratings right up at the top here, collector emitter voltage. That's what I was talking about before. The BC547 is rated for 45 volts, so the 3 volts that it would see if I use an LED as a flyback diode will be fine. Awesome. All right, so it's about time we actually do some soldering. So let me grab all the flat components that I'll put in first, except for you, and maybe except for you. Now we'll put the Schottky diode in. So resistors first. I know that these are the 470s. I know what that is. That's not a big deal. We have 3 other anonymous resistors here that we need to quickly work out where they belong. So you could take a multimeter and measure the resistance across them. I'm going to go off the color coding here, which is from right to left. And I know it's right to left because the gold band is the tolerance. The tolerance you can think of as the last band you should be looking at. So I'll flip it around for left to right. We have, come on, focus, yellow, purple, and red. So 470 was yellow, purple, and brown. This is yellow, purple, and red. So that's 4, 7, and then 2 zeros, or 4.7K. In the schematic here, we see R5 is 4.7K. So I'm just going to bend the leads like so and find R5 on the silk screen. There it is. And I should probably not bend them so close to the resistor because the holes are spaced out a little wide. That's okay. I'm going to bend the leads a little bit out like that so it won't fall out as I keep placing the rest of the the resistors. Next resistor. Pull this up. Take a look. Gold is on the right side, so read it left to right. That is 4, 7, and then it's a black band. That's 0, 4, 7, and 0 zeros. This is a 47 ohm resistor. I should really call this the 47 game. All right, then that goes in R7. So again, I'll bend the leads this time. I can bend them a little bit farther apart. You don't need to keep them so close to the resistor. R7. There is R7. And no surprise, R7 is right next to D1. If we look on the schematic, we see D1 and R7, and then there should be a D2 somewhere. Is that nearby? Well, it's over here. We'll worry about that later. Last single loose resistor here is 4, 7, and 2 zeros, 4.7K. Or we had a second 4.7K? Yes, we did. R6 right there. So why didn't they just have 2 4.7s wrapped in tape like that? R6, right? R6, yes, R6. And there's no polarity to resistors. They can go any way, backwards or forwards, doesn't matter. Although if you have a bunch of resistors lined up next to each other, it's just more visually pleasing if they're all going in the same direction. And then we have R1 through R4, these 470 ohm resistors. Where are they? R1, R4, R2, and R3. And what I'm going to do first is just cut these off like so. You could pull the leads out of the tape, but what happens is there's a little bit of residue. You see that on the tip there of the glue from the tape. And that, when you're putting the component through the hole, you could leave a little glue behind. And that might screw up the joint when you solder it. 99.9% of the time it'll be fine. You don't have to really worry about it. But I feel like I have to point that out just so for that 0.1% who try this and the joint breaks or they get a bad joint because there's a little bit of glue in there. Well, there you go. That's why, and that's how you avoid it. And then I am going to put that Schottky diode in here. I don't trust the future people who find this device years from now, and perhaps they don't have batteries like that in the future, and they'll wire it up backwards. And oh no. So that is D1, and there is polarity. That black band, there we go, needs to match up the white band down here. Like so. Alright. Let's start soldering. So I'm going to flip this upside down. Bring in my iron. I will quickly tin the tip just to help clear off any oxidation that's on there. That would prevent good soldering. And just ham-fistedly apply solder, because this does not have to look pretty or precise. All you have to worry about is making a good electrical connection. If I angle this camera differently, or maybe I just angle the light differently so you don't get all that reflection off of it. So part of the trick here is not being impatient. It's not about just filling, putting your iron next to the lead here and then sticking the solder on the iron and turning it molten. You need the lead to get hot. You need the pad that you're soldering to get hot as well in order to make a good connection. So it usually takes a couple of seconds. Just leave it there. Try to get both the iron tip touching both the pad and the lead. Leave it for a couple of seconds and then bring in the solder. And hopefully it will flow naturally on its own. Hopefully. Some will take more time to heat up and get the solder to flow than others. That is a product of thermal mass. What does that mean? It's like the difference between trying to heat up, say, how do I want to, what's going to be a good analogy here? Let's say you have, I don't know what a good analogy is. Let's just go with, the more metal you have, the more heat to get the metal up to temperature you need. So how about if you have, how about we use soldering irons as an example. Let's say you have a soldering iron and it's very small. It will probably come up to temperature very quickly. But if you have a giant soldering iron, say the size of a baseball bat, it's going to take a lot more power to heat up an entire baseball bat to the same temperature as it would as this small soldering iron. And the difference between the two is the thermal mass, the amount of mass that you need to heat up, and the energy it's going to take to heat that material up to that temperature. Does that make sense? No, I am just rambling, because I have not yet mastered the ability to both walk and chew bubblegum. I'm working on it, though. Come on. Now, to make life easier, you don't have to solder everything before you start clipping leads. Solder a few things, then clip the leads off. That way they're not in your way when you're soldering the other leads. But I'm being lazy. Okay, now if you are soldering and you get to this point where you need to clip some leads off, grab a little container of something. This is the top off of, I don't know, a thing of shaving cream, I think. And just clip the lead and collect them in here. Why? These leads later on come in real handy when you need to make connections, when you need to make links on a PCB. If you have like a little gap somewhere and you need to connect the two sides together, you just grab a lead, a little leftover strip of metal from this, and you are all set. Instead of having to go and buy stuff like that. So there's all sorts of things that you will read about when it comes to soldering and then cutting these leads, like don't cut into the joint, cut above the joint, yada, yada, yada. Don't worry about it. Just clip right into it. If you were producing or working on a device that was going to be used in, say, a satellite or, anything that's going to be used more than by yourself in a hobbyist environment, yeah, that's something you should do. You should be careful with how you cut the leads because you don't want things to go wrong when the item is 20, 30 years old and a million miles away. But for our purposes, you don't need to worry about that. Just clip the leads. Don't worry about how close you're clipping them. Alright, what's next? I like to work from shortest to tallest components. Are the buttons going to be next? Do I want to figure out the D2 situation? The way I figure this is going to work is I am going to wire... I need a resistor. I need to go find a resistor. We'll do that. We'll do that last. Actually, this will come last. D2 will be last. So what's the next shortest thing? I think it's the buttons. Doesn't look like we have to worry about orientation here. For the buttons, they can only go in one way, really. Well, two ways. You can flip them around like that, but they can't go in that way. So you don't have to worry about orientation. Just slap them in. Like so. They hold themselves in place nicely. And we'll just solder it all together. In theory. I am using a very small diameter solder here, so I have to throw a ton of solder in here to get the joints, especially these big buttons. You do not need to use a small diameter solder. I think this is like 0.2 inch diameter. Or is it 0.022 inch diameter? I think it's 0.22 inch diameter. Why do I use such a small diameter? Because I sometimes work with surface mount stuff, so I want a small diameter. And I'm too lazy, or I don't care enough to have multiple rolls of solder with different diameters. I'll put in the extra work, and if I have to throw a couple inches of solder into a big joint like this, so be it. Not a big deal. Whereas, if I only had a very large diameter solder and I needed to work with some kind of surface mount deal, things become much more difficult. And that's not as easily solved in that scenario as it is having big joints and a small diameter solder. Good. What's next? How about this capacitor? What is this capacitor for? This is the call it a bypass capacitor or the power supply capacitor for the microcontroller. It just goes right there. Come on, just throw solder at it until it fixes itself. Do I care about how pretty it looks on the other side? You know what? I sort of do. Aesthetics. You don't have to. Aesthetics don't matter. Electrons will flow happily no matter how pretty or ugly things are. That's the nice thing about electrons. But I care about the presentation, which is why I will try and make that look straight and even. What's next? How about a transistor? There's only one, and it goes to T1. We can see that this transistor has a curved section and a flat section. The silk screen on the PCB has a flat section and a curved section, but instead of 3 holes next to each other, the middle hole has been pulled back a little bit. So that has to be done to this transistor. Get out of the way. So there's an option here to focus on it. I'm going to pull this back like so. I think I'll spread these out a little bit. Like that. And we'll see how bad I was. Pretty bad. There we go. Focus. There. And I could leave it that high. I could try pushing it down further if I wanted to, but there's no point in stressing the joints too much, so I'll leave it like that. Or not joints, the legs of the transistor. Well, the joints inside the transistor, where the legs connect to the actual the internal structure, actually they just connect to the plastic. The plastic housing is going to hold it in place, provide mechanical stability, and then there'll be tiny little gold wires connecting from the ends of these leads to the actual silicon die where the transistor is laid out. Okay, what else? The buzzer. This is polarized, or it claims to be. We can see a plus and a minus there. The long lead is the plus side, and oh, it's even got a mark on top, which you can't see because I've manually focused the camera. Oh well. I should probably do the socket actually first, because that's going to be a little bit shorter. Yep. What am I? Oh, the transistor is tall too. Oh, well, I screwed that up. I should have put the socket in before the transistor. So what I'll do is I will solder this leg, just one, and I'm with my finger holding the socket and pushing it toward the PCB to reflow that solder so I can then push the socket flat. I'll solder the opposite leg like so. Confirm it's still flat. Yes, good. If it wasn't flat, I would reflow the solder and keep pushing until it was flat against the PCB. Go, go, go. Flow, solder, flow. Okay. Now we can do the buzzer. And we still have that flyback diode. Do not let me forget that, because that is kind of critical. We do not need 40-volt spikes blasting away at the transistor. For diodes, 4 LEDs. I should probably have put those in before the buzzer. I've screwed up yet again. So if you look at the symbol here for the diodes, you've got a circle, but one side is flat. That's the negative side. Look at the LEDs themselves. The short leg is the negative side. There's also, focus, you son of a, there's also a flat space on this LED at least. Some LEDs won't have that flat side to let you know which is negative also. So you usually go off of the length of the leads. Like that. Focus. I could do fixed focus, but the problem is then every time I want to get a close-up, I have to keep refocusing. Okay, that is good enough. Flip it over. And I'm only going to solder one leg on each so that I can, like the socket, then reflow while I push from the other side to get the LED flat against the PCB. So it, again, looks pretty. You don't have to. You could have your LEDs pointing in all sorts of different directions if you are someone who enjoys introducing chaos into their electronics. See, like if you like wonky LEDs, you could leave it like that. I don't. I have a desire to make this look organized, like some thought and care went into it, even though, as you are discovering, very little thought goes into this. Just looking, everything looks flat, everything looks good. Now, what am I going to use for a resistor value on that flyback LED? Which I don't even know if that's legal. I don't know if I'm supposed to be able to do that or not. We're going to find out together. Again, part of why you have a kit, to experiment. And if it breaks, I don't care. This is just my trash soup bowl here. I'm dumping my leads in there because I showed you I already have 4 million things of leads in that little shaving cream cup top thing. You're not seeing anything. See, just, and then I'll throw this away once it starts to fill up with junk. I should probably cut the lead on the speaker. That's fine. Good. All right. Oop. Pardon, you were in the way there. All right. What's left? Well, we need to put the battery pack in, and we need to wire up this LED. How am I going to do that? Okay. So it's going to conduct as soon as 3 volts is going through it. Could I get away with no LED, with no resistor? I don't think so. I think I want a slow value resistor. I think I want something like, I probably don't need anything more than like 47 ohms. I'm going to go see if I have a 100 ohm resistor. One moment. My drawer of many random resistors. These are all 470s that I bought off of eBay. Some of these are marked, some of these are not. That's an orange band. I can tell it's a 10K. Or is that 100K? Red, orange. Yeah, that's 10K. 1 mega ohm, 10K. 220 ohms. That is a possibility. I see the blue. That's telling me that's going to be... What is that? Red, orange, yellow, green, blue. What is that? Is that 680? That's a weird number. 10 ohms. I see you. I see you. 10 ohms. Yes, perfect. Do I want 10 ohms? I wanted 100 ohms. That's 100 ohms. There we go. sometimes, focus, the letter R is used to denote ohms because the ohm symbol and the letter R are kind of the same or look the same if you're really, really lazy, which a lot of people are. Okay, how am I going to do this? I'm going to cut. How do I want to do this? Some thought needs to be had. Where is... Grab me a little pair of pliers. Come, think with me. So I'm going to attach it to the negative side. The resistor can go on either side. It doesn't make any difference. So I'm going to bend the lead out like that. It's going to go like that. Do I want it to be like that? Because look how close it is. I don't want it to be like that. I'm going to bend this out like so. Bend that down like so. Yeah, something like that. And then that can come up. That'll be like that. Yeah. Yeah. So this I'm going to cut here, like that. Now I need helping hands. Come here, you. Put this in like so. And I'm going to flood that spot with a bunch of solder. I want a blob of solder. Good enough. You can go over here and wait. Bring in the resistor, chop that off right there. I have no idea if 100 ohms is too much or too little. I really don't know. Because what's going to happen is it's not going to be like a 4 or 5 volts. It's going to, as soon as it starts conducting, the voltage, it'll be the forward voltage. So it's going to be, I probably should have gone with 10 ohms, but so be it. I probably should have gone with 10 ohms. Okay, how am I going to solder this now? I did not think ahead. Can I do something really stupid here? That would hurt so much if I did that. Yeah. Yeah. let's see how that works. I have my suspicions that I should have used a much smaller. I should have gone for that 10 ohms. I think I'm going to be annoyed with myself. We're probably not going to see much of anything. We'll find out. Again, this is all about... This is part of what electronic kits are all about. It's experimenting. Now, I probably could sit down and go online and do maths and identify what the right resistor is for that, but you know what? This video is already, I don't know, an hour at this point. Okay, so really all that's left now is the battery pack. Now, the way it has this going together, and I'm going to screw in the battery pack before I solder anything. You notice how the leads here for the battery pack, you notice how it seems to hint? The leads are together and they're not. Those lying sons of a so-and-so. Oh, and that's not even good either. Look at that. This is the positive, but it's clearly marked negative here. Oh, I don't like this at all. That's terrible. That can't be how you decided it. Is it? It is. Look at that. The positive terminal... And if I flip it around, is that the negative terminal? Okay, so maybe we do that. Okay, never mind, that's fine. Crisis averted. So it has to go in like that. There are spacers that are going to go between the PCB. And I'm going to have to go get a length of wire, because what I need to do is wire that from here through this channel. Not even that. What is going on here? Oh my gosh. So I'm going to do that. I'm going to do that. Really? That's how you're going to... I disagree completely with how this thing has been arranged here. So we're not using that channel. That won't make any sense. And that lead is not going to be long enough. I need wire. I need wire. Wire acquired. I think this is 28 gauge solid core. Anything would work, but I could even have used those clippings, but I am not a masochist or a sadist towards myself, which makes you... These are terms I'm not quite familiar with. Okay. Do I want to screw this down before I wire everything up? Yeah. Yeah, I do. Because I don't know how things are going to... I don't know how what the length of wire that I'm going to need is going to be, so I should do this. That spacer, that is a massive gap there. Come on, just want to get this thing started so I can let go and it won't fall apart. Oh, Oh, no. No, the better way to do this is to actually get a stupid screwdriver, like so. Hold it like that. Come on. There we go, I think. No. I'm sure there's an easier way to do this. I have no clue what that is. Come on, you threaded. The first couple of turns should be fine. Good enough. Now how am I going to get that in there? I am not thinking this through at all. Oh, it's just a mess now. Fumbling around with this with absolutely no clue how to do this. Again, I have no doubt there is a far easier way, and I just am not seeing it right now. That doesn't even want to go in the hole, does it? No. There we go. Alright, go back up now. I don't need all of you. Good enough. Yes, yes, yes. Oh, yes. Yes. Oh boy. A socket. Million times easier. Oh, come on. Oh, you've... Can't use that. That's ceramic. That will crack. Oh, no. Oh, actually. Okay. That might be the way to do it. Or maybe not. Like, oh, you son of a... Oh, boy. What am I screwing into there? I have no idea. But somehow... The PCB? Is that what that's screwing into? Oh, does that mean that this is... I think I need to start it before I can bring in the socket. Why are you at an angle? You shouldn't be at an angle. This is why electrical engineering is better. What are the gap? The gap is just ridiculous. All right, whatever. Whatever. It's these moments that you're not supposed to show, where you're 80% of the way through this and one or two things start to go a little bit weird, and the energy that you had when you started just isn't as vibrant as it is now. But we persevere. We persevere. All right. I'm going to flood the heck out of those. No, I'm not. No, I am not. I will bend this up. I will cut one of these spare leads off, like so. Bend that like so. Like that. Like that. There we go. A lot of thermal mass here. Okay. I don't know why I'm using these ceramic tweezers, because it's just, that's what I had in front of me. Snips. Cut you off right about there. Come on. Don't be shy. Yeah. Yeah. Well, let's just double check that. That is the negative side. That is the negative of the battery terminal. Okay. That would have been freaking hilarious if I came this far and I screwed it all up by getting the wrong terminal. Okay, this is going to take a lot of solder. I mean, we are talking a boatload. This is when you want the thicker, larger diameter solder, because, yeah. But that should do it. We have a negative battery terminal connection. All right. Positive side now. You're in my way, Mr. Light. Okay. I'm gonna do a rough cut right there. Going to to strip the end. Oh, it's not 28 gauge. It's got to be... What gauge wire is it? Surely it says on the side here. AWM, 300 volts. 300 volts. FT1. I'm sure one of those means something. I'm going to go with its 22. Sure. Now I need to solder that to that. Little hook. Sure, that works. I'm just interested in, ow, solder splash on my hand. So solder contains flux, which is chemical that sort of, or chemical cocktail that helps clean the surface, gets rid of the oxides and stuff, makes better solder. The problem is it also will spit at you from time to time. And what are we at? 650 degree Fahrenheit. Spittle on your hand does not feel great. I know that is a shocking revelation. Alright, so I'm gonna run you over here. You're gonna make a turn right about there. Cut you there. And then strip the wire from the turn. There. Perfect. Of course, now I have to realign everything. Make that bend again. In fact, I'm going to do that. Let's see, it wants to stick out. I need to fiddle with this until it's... Is that? Okay. Thought I saw some issues with the insulation. Might have been cut, but it wasn't. I'm going to get that. Come on, get in there. Give me something that I can angle that in. Good. Good. Tweezers. The unreasonable ceramic ones. And just as expected, the realization sets in that I turned it a little too... There we go. Oh my gosh, it almost fits. Look at that. It's... Oops. Focus. It's like I planned it. Okay. Now we just need to focus. And get in here with, again, just an epic amount of solder. Just need it to, come on, start flowing, heat up the pad. There we go, yes. Okay. There's no on-off switch. So when the batteries are plugged in, it's always on. Brilliant. PIC microcontroller, if it goes into sleep mode, in theory, should only be eating up like nanoamps, so amps of electricity. So that shouldn't be an issue, assuming it's been programmed correctly. Just cleaning up my space here a little bit, because we are done. or like 99% of the way done. I need to find batteries. Batteries acquired. However, there is one final step that I have not shown yet, which is we need to put the chip, the PIC microcontroller that has all of the logic in there. Now, when I pull this out, you will see that the legs are not perpendicular. They splay out like that, and I need them to be straight. There's a couple of ways to fix that. I could put it on the surface here and roll it forward like that to try and straighten them out, or get one of these. These were like $5 off of eBay, and it straightens the pins for you. You just put it in there like that, give it a couple of squeezes, and we've got perpendicular pins. That thing, I didn't know it existed. I saw another video on YouTube where somebody used one, and I immediately went and found one, and it has been the most useful thing, because not only will it take new chips and, straighten the pins out for you, but it'll also take chips that you've pulled out and wrecked the pins on, and it'll re-straighten them for you. It's very beneficial. Okay, so time to put batteries in here. Now, when I make this connection, will it explode? Nope, but it's letting us know that it is on. Now, I don't see anything in the flyback LED diode here. That's because it should only light up, in theory, if it's going to light up at all, when the buzzer is going. Alright, so I have to pick sound or no sound. I'll pick sound. Did you see that light up? The flyback diode doing its thing. Oh, it works. The little flyback diode LED thing works. So you can see when that diode is actually being used. That is wonderful. Alright, so I guess we should play a game now. Alright, so music or sound, level 1. It's a Simon Says. That's what this is. Or a Simon, whatever that game is. Oh, shoot. Oh, I guess that means I won. Alright, music, level 4. Nah. But that little LED is actually working great as the flyback diode. That might be the wrong term for it, calling it the flyback diode. I've seen it called a lot of different things. Wow, that's close to that screw there. Not that that would do anything, but oh well. So every time that lights up, that is the transistor has turned off, and the stored energy in the coil in the speaker is dissipating through that diode. So So every time you see that light turning on, that's energy that would normally have just been thrown away. But now you get a little extra light effect with it. Yeah, so that is the brain game. And that came out really nice. I am actually happy with how the mods work. The yellow LEDs are bright. It's not a big deal that I didn't have to change the resistors for the LEDs. That stupid little flyback LED is absolutely tickling me. The standoffs are a bit weird, and I didn't like how the battery pack is connected to the PCB. Those two things they feel like an afterthought. But yeah, that works great. That is the Velman Brain Game. Bring in the card for a end shot. Wow, look at that. Now I just need to find 3 other people so we can all sit around a table and look like we're doing business when we're really playing a silly game.